Imagine like trying to calculate the light bouncing off a million different surfaces in a virtual room, and you have to do it, 60 times every single second.
Right, which is just a staggering amount of math.
Exactly. If you calculate every individual light ray bouncing from a lamp, hitting a wall, scattering into the dust, and finally reaching the camera, if you try to brute force that literal physical reality, your GPU will simply melt.
It would just instantly thermal throttle. Yeah.
Yeah, so graphics engineers don't do that. They use a cheat code, a mathematical shortcut that compresses the entire lighting universe of an environment into just a handful of numbers. And today, we are completely tearing open that cheat code.
We really are.
Welcome to a custom-tailored deep dive, specifically designed for you, the low-level programmer, the AI engineer, the person writing the web GPU shaders. Our mission today is to totally demystify the mathematical bedrock of modern 3D rendering, global illumination, and cutting-edge pipelines like 3D Gaussian splatting. We are talking about spherical harmonics.
Or SH, as you've undoubtedly seen it abbreviated in like 100 different GitHub repositories by now.
Oh, absolutely. It's everywhere.
It is. And it's a topic that sounds incredibly intimidating, honestly. It sounds like abstract quantum physics, and as we'll uncover, it actually owes its very existence to quantum physics. But for you, the graphics programmer, it is arguably the most indispensable tool in your entire arsenal.
It really is. So we've got a massive stack of sources to pull from today to make this actually make sense. We are synthesizing heavy university physics text on electrodynamics, a really brilliant algebraic theory paper out of Reed College, and hardcore computational graphics guides that detail how these abstract mathematical functions are actually implemented in GPU memory.
Which is the crucial part, bridging that gap between the theory and the metal.
Right. And the reason you need to stick with us through the math today is because of how fundamentally this transforms your code. In 3D Gaussian splatting, for example, the training phase treats spherical harmonics as this continuous, multidimensional feature space to resolve neural artifacts. But then the rendering phase completely flips the script and treats those exact same functions as a static, pre-computed lookup table.
What's really fascinating here is that dichotomy. You have a highly dynamic gradient descent optimization problem during training, and then a blazingly fast algebraic evaluation during rendering.
Yeah.
But to truly leverage that trick, to optimize your shaders so they don't bottleneck on ALU operations, you cannot just copy-paste a library function. You really have to understand where these harmonic functions actually come from.
You have to know the roots.
Exactly.
Yeah.
And that means we have to start at the absolute foundation of physical mathematics. We have to talk about partial differential equations.
Okay, well, let's unpack this. Because to get to spheres and lighting and 3D space, we first have to talk about a symbol that honestly haunts the nightmares of anyone who ever took a multivariable calculus class.
Oh, I know exactly what you're going to say.
The upside-down triangle squared, the Laplacian operator.
The dreaded Nablus squared, yes. It is the absolute heart of fundamental physics. If you look at the heat equation, which dictates, how temperature disperses through a solid metal block.
Right.
Or the wave equation, which governs everything from ocean swells to acoustic vibrations. Or even the Schrödinger equation in quantum mechanics, which tells you where an electron probably is. They all rely entirely on the Laplacian.
Wow, okay.
But specifically for graphics, we are interested in Laplace's equation itself, which is beautifully simple. It is simply the Laplacian of phi equals 0.
Right, where phi is just some function, some arbitrary field. Now, mathematically, the physics texts define the Laplacian as the, quote, divergence of the gradient of a function. Let's translate that into programmer speak, because divergence of the gradient sounds like total word soup.
It does, yeah. Let's break it down into two distinct steps. First, the gradient. If you have a scalar field. So imagine a 3D grid where every single voxel just holds a single temperature value. The gradient is a vector that points in the direction of the steepest increase in temperature.
It's the slope.
Exactly. If you are standing on a hill, the gradient points straight up the steepest part of that incline.
So in graphics, the gradient of a surface is essentially tied to our normal vectors. It tells us which way the surface is fundamentally facing.
Precisely. Now, the second step is divergence. Divergence measures how much a vector field is spreading out from a specific point or converging into a point. It's a strict measure of sources and sinks.
Okay, so like a faucet or a drain.
That's the classic analogy. If you have a vector field representing water flow, a faucet has high positive divergence, and a drain has high negative divergence.
So the Laplacian, being the divergence of the gradient, is essentially asking how much are the steepest slopes spreading away from this specific point?
Right.
Which implies we are looking at how the slope of a slope is changing. We are looking at the 3D curvature. But the sources gave this incredible geometric intuition that I think makes it click instantly, especially if you write like image processing
Oh,
kernels.
the neighbor averaging concept. I love this.
Exactly. It's so clean. Imagine a function, let's keep calling it phi mapped out, on a standard 2D grid, like a grayscale image in memory.
Yeah.
If you pick a specific pixel, draw a little circle or a disk around it, and calculate the average value of all the pixels on the boundary of that disk, the difference between that boundary average and the value of your center pixel is strictly proportional to the Laplacian.
And the math bears this out beautifully. The formula derived in the physics text notes that the average of phi along the boundary minus the center value of phi equals 1 over 4 squared times the Laplacian of phi.
Where r is just the radius of your sampling disk. Right.
Exactly.
So what does this actually mean for Laplace's equation? If we set the Laplacian to 0, meaning nabla squared phi equals 0, we are mathematically asserting that the difference between the center and the surrounding average is 0.
Right.
The value at any given point is exactly the average of its surrounding neighborhood.
If we connect this to the bigger picture, it means the field is perfectly relaxed. There are no artificial peaks, no unnatural valleys, there's no stress in the system. The value at every single coordinate is in perfect harmonious equilibrium with its neighbors.
I want to throw an analogy at you to see if this holds up. I picture the Laplacian as, like, a tension detector in a stretched rubber sheet.
Oh, I like that.
Yeah, so if a point on that rubber sheet is physically pushed higher or pulled lower than the average height of the rubber immediately surrounding it, there's tension. The rubber sheet naturally wants to snap back into place. It's not relaxed.
That's a phenomenal way to visualize it. If it is not relaxed, meaning if the Laplacian of phi does not equal 0, you get a restoring force. The physical properties of the rubber sheet are actively trying to push that isolated point back to the local average.
And it snaps back.
Right, and basic physics tells us that if you have mass and a restoring force, you get acceleration. That acceleration immediately leads you to the wave equation. But Laplace's equation, set to 0, describes the steady-state, fully relaxed phenomena. It's what happens after the rubber sheet stops vibrating. Think of electrostatics, or irrotational fluid flow, or gravity in empty space. Once the physical system has settled into its minimum energy state, it universally satisfies Laplace's equation.
Okay, so as a programmer, I'm extremely used to working in a 3D grid to calculate these things. Voxels, arrays, Cartesian coordinates, X, Y, and Z.
Standard stuff.
Yeah, and it is incredibly easy to picture this neighbor averaging in a box. You just loop through x minus 1, x plus 1, y minus 1, y plus 1 in a compute shader. So my question is, why do we need to abandon Cartesian coordinates to solve this lighting problem? Why make it so mathematically painful by moving away from boxes?
Because while Cartesian coordinates are great for drawing boxes and allocating linear arrays in memory, the physical worlds and the rendering environments you are trying to simulate do not revolve around boxes. They revolve around spheres. Think about a point on a surface in your 3D scene. When you calculate global illumination, light isn't hitting that point from a cube. Light is hitting it from a surrounding hemisphere of incoming directions. Planets are spheres. Atoms are spherical. The skybox wrapping your level is a sphere.
So form follows function.
Exactly. If the physical geometry of your problem possesses spherical symmetry, forcing a Cartesian XYZ grid onto it will create boundary conditions that are essentially unsolvable. The math will just fight you every step of the way.
You'd have jagged edges everywhere.
Yeah, you will have jagged edges of boxes trying to approximate a smooth curve. You're fundamentally forced to change your coordinate system to match the native geometry of the problem.
Which means we have to leave X, Y, and Z behind. We have to completely pivot to the spherical coordinate system. This is where we adopt R for the radius, or the distance from the center. We adopt theta for the polar angle, often called colatitude, dropping down from the North Pole toward the South Pole. And we adopt phi for the azimuthal angle, which is like longitude wrapping horizontally around the equator.
And this transition is where the math gets notoriously, famously messy.
Oh, it's brutal.
It really is. When you take that elegant, simple little Laplacian operator, label squared, and you translate it into spherical coordinates using the multivariable chain rule, it expands into a massive, intimidating differential equation.
I was looking at it in the source text, and it genuinely looks like a typo that just kept going.
It truly does. You suddenly have 1 over r squared terms multiplied by nested partial derivatives with respect to r. You have sines and cosines of theta tangled up with derivatives of theta. You have second derivatives of phi divided by r squared sine squared theta.
It's a nightmare.
It looks completely impenetrable. It looks like something a computer algebra system should solve, not a human being.
But mathematicians have a standard weapon for this, right?
Yeah.
The texts outline a technique called separation of variables, and it feels, honestly, almost like cheating when you first see it.
It does feel a bit like a magic trick.
Yeah.
Yeah.
You make this massive, bold assumption. You assume that the final, highly complex solution, let's call it psi, a function of r, theta, and phi, can be perfectly factored into 3 completely independent one-dimensional functions multiplied together.
Right. And this raises an important question. Why would we ever assume that's possible? But you're right. We assume a solution of the form capital R of R multiplied by capital theta of theta multiplied by capital phi of phi.
Yeah.
You are assuming that the radial fall-off of the light has absolutely nothing to do with the angular pattern of the light.
Which, in the context of an environment map that's infinitely far away, actually makes intuitive sense.
Exactly.
The pattern of the clouds in the sky doesn't change just because you walk 2 feet forward in the game world.
That's exactly the physical intuition justifying the mathematical leap. And here is where the algebraic magic happens. You take that factored trial solution, r times theta times phi, and you plug it back into that massive, messy spherical Laplace equation.
Okay.
Then you perform a critical maneuver. You divide the entire massive equation by the trial solution itself.
Wait, you divide the equation by the solution you're actively trying to find?
Yes, and because of how the partial derivatives work, it's a total stroke of genius. The derivative with respect to r only affects the r function. The theta and phi functions act like constants in that term and just sit there.
Oh, I see.
So when you divide by r times theta times phi, the theta and phi cancel out of the radial term entirely. You end up perfectly isolating the variables. You can algebraically rearrange the entire equation so that everything containing an r is strictly on the left side of the equal sign, and everything containing a theta or a phi is on the right side.
Okay, I see where this is going. Since r can change completely independently of theta and phi-like, you can move further away from the center without changing your latitude or longitude. The only mathematical way a function of purely r can always equal a function of purely angles, no matter what values you plug in, is if both sides equal a constant number.
Precisely. Think about it. If the left side only knows about radius and the right side only knows about angles, they can't dynamically adjust to match each other as you move around. They must both be anchored to a constant value.
That's incredibly elegant.
It is. You have successfully split one impossible 3D partial differential equation into independent, highly solvable 1D ordinary differential equations. The radial part equals a constant, and the angular part equals the negative of that same constant.
And looking at the sources, they denote this first separation constant in a very specific, weird way. They don't just call it C, they call it L times L plus 1, where L is a non-negative integer. Then they take the angular part, which still has theta and phi mixed together, and they do the exact same separation trick again. They move phi to one side, theta to the other, set them equal to a second constant, and denote that second constant as m squared. No, I have to push back here. Why L times L plus 1 and why m squared? Why not just call them C1 and C2? As a programmer, seeing someone write L times L plus 1 just looks like mathematicians trying to make things look prettier in hindsight because they already know the final answer. Is that what's happening? Did they just reverse engineer the notation?
It's a very fair point, and yes, historically, the notation was chosen in hindsight to make the final resulting formulas cleaner. But, and this is absolutely crucial, the form of those constants, the reason they are strictly constrained to integers, is dictated by hard physical geometry. They aren't arbitrary.
Okay, prove it.
Let's look at the second constant, m squared. When you separate the azimuthal equation, the longitude, see it simplifies into a basic simple harmonic oscillator. The equation literally says that the second derivative of the phi function equals negative m squared times the phi function.
So the slope of the slope is proportional to the negative of the position. That's a wave.
Exactly. It's the standard equation of a swinging pendulum or a vibrating guitar string. The mathematical solutions to that are sines, cosines, or, more broadly, complex exponentials like e to the power of I times m times phi.
Right, Euler's formula ties those all together, but why does m have to be an integer? Why m squared instead of just a random decimal constant c?
Remember what the variable phi represents in our physical space. It's the longitude. It wraps all the way around the sphere.
Yeah.
So if you pick a point in your 3D scene at a specific angle, and then you do a full 360-degree rotation, meaning you mathematically add 2 pi to phi, you are physically standing at the exact same point in space.
Yeah.
Therefore, the mathematical function must evaluate to the exact same numerical value. It must be perfectly periodic.
Ah. If you plug in phi equals 0 and phi equals 2 pi, the output of the function has to match perfectly. Otherwise, your skybox literally has a visible seam where the values tear apart.
Exactly, you'd have a massive discontinuity in your rendering. For the wave function e to the im phi to be periodic and match perfectly at 0 and 2 pi, m absolutely must be an integer. It can't be 1.5, or the wave would be halfway through a trough when it meets its starting point. It would tear.
That makes perfect sense.
So m has to be 0, plus or minus 1, plus or minus 2, and so on. That geometric reality forces the math. And similarly, the ln times L plus 1 structure arises because solutions to the polar angle equation, the latitude will spiral out to infinity and break at the north and south poles unless L is strictly an integer. The physics enforce the integer constraints.
Which elegantly transitions us to how we actually solve that tricky polar angle part. We've separated the variables. The radius part, r, is basically handled. The longitude part, AFI, is just a standard complex exponential wave. But the theta part, the colatitude dropping down from the pole, is the real beast.
It is, without a doubt, the most mathematically demanding part of the derivation. Solving the theta equation requires a very clever change of variables. The sources detail substituting omega equals cosine of theta.
Stop right there. Why make that substitution? Whenever I see a math paper pull a substitution out of thin air, I immediately want to know what it achieves algorithmically. What is the actual goal?
It's all about bounding the domain. The angle theta goes from 0 to pi radians. By substituting omega equals cosine of theta, you map that angular domain to a strict numerical range between 1 at the North Pole and -1 at the South Pole.
Oh, wow, that's brilliant. It turns a cyclical trigonometric problem into a linear algebraic space strictly bounded between -1 and 1.
Exactly. And when you run that substitution through the differential equation, it transforms into a well-known, heavily studied format called the associated Legendre equation. And the solutions to this equation are the associated Legendre polynomials, denoted as p sub L superscript m of cosine theta.
Legendre, a name that strikes fear into the hearts of engineering and physics students everywhere.
Oh, absolutely.
But basically, these polynomials are just predefined mathematical curves that smoothly map values between -1 and 1, ensuring the function doesn't just blow up to infinity at the poles.
That's a perfect functional description. And when we combine that theta solution, the Legendre polynomials, with the phi solution, the complex exponentials, we finally, after all that brutal calculus, arrive at the complex spherical harmonics, denoted as y sub L superscript m of theta phi.
Okay, let's break down those indices, L and M, because if you are writing code for 3D Gaussian splatting, L and M are basically the API parameters for this entire function.
They define the literal shape of the harmonic. The degree, L, which ranges from 0, 1, 2 upwards, dictates the overall spatial frequency of the harmonic. The higher the L, the more complex and detailed the physical pattern.
It's the resolution knob.
Yes, exactly. And the order, M, which ranges from -L up to +L, dictates the subpatterns. Specifically, it determines how many times the function oscillates or waves as you wrap around the equator of the sphere.
Now, when you look at the raw formula for YLM in the textbooks, there are some weird constants attached to the front of these polynomials. There's this massive square root for normalization, which, makes sense to keep the values constrained.
Right.
But there is also something called the Condon-Shortley phase, which is just a -1 to the power of m, multiplied at the very front. Why multiply by a random alternating -1?
If we connect this to the bigger picture, that phase is a historical convention imported directly from the birth of quantum mechanics.
Really?
Yes. In quantum physics, when you are dealing with the angular momentum of an electron, you have these mathematical constructs called ladder operators. They literally step an electron's angular momentum state up or down.
Oh.
Adding that specific -1 to the m phase to the harmonic function ensures that when you apply those ladder operators, the resulting mathematical constants remain purely real numbers without generating messy imaginary numbers that would overly complicate the physical interpretation.
That is mind-blowing to me. It highlights how heavily modern graphics programming borrows from mid-20th century quantum physics. When we render like a shiny sports car in a video game, we are using the exact same mathematical basis functions that physicists use to describe the probability clouds of an electron orbiting a nucleus.
It's amazing, isn't it? The math doesn't care what you apply it to. A spherical probability field and a spherical lighting environment map are fundamentally structurally the same mathematical problem.
I want to ground this for the listener with a more familiar analogy. Think about regular 2D Fourier series. If you've ever done audio processing or basic signal analysis, you know that you can build any repeating 2D waveform, a harsh square wave, a jagged sawtooth wave, whatever, just by stacking simple, smooth sine and cosine waves of different frequencies on top of each other.
The trigonometric basis, yes. By adjusting the amplitude of each frequency, you can approximate absolutely any shape.
Right. Spherical harmonics are just the 3D spherical equivalent of a Fourier series. They are in orthogonal basis. You can build any continuous function on the surface of a sphere like the incoming light from an insanely complex high dynamic range skybox by stacking these harmonic Legos together.
That is precisely what they are. The YLM functions are the strict spherical equivalent of sines and cosines.
But here's where it gets really, really interesting. We just spent 20 minutes talking through this grueling calculus process. Partial derivatives, variable substitutions, Legendre polynomials. If you had to write a program to derive that from scratch, it would be a total nightmare.
It would be awful.
But the sources outline a fascinating twist in the mathematical history. There is a way to bypass that calculus entirely. Let's talk about the algebraic alternative, Cramer's construction.
This is one of those elegant mathematical backdoors that you almost can't believe works until you see it on paper. The traditional derivation we just discussed is incredibly heavy on calculus. But in 1996, a physicist named Nicholas Wheeler at Reed College published a highly detailed breakdown of a method originally pioneered by Hendrik Kramers. Kramers was a brilliant physicist who looked at this problem and took a purely algebraic route.
He basically looked at the calculus and said, no thanks, there's a better way.
Exactly. Instead of starting with a massive spherical Laplacian and trying to separate variables, Kramers assumed a factored structural solution right from the very start, but he did it in standard Cartesian space. He proposed a solution of the form pii of x, y, z equals f sub L of r multiplied by a dot r, all raised to the power of L.
Okay, let's break that equation down for a second. F sub L of r is just a radial function. R is the position vector, x, y, z. That part is pretty straightforward. But what is this vector A?
Vector A is just a constant 3 vector. It has an x, y, and z component. But here is the absolute genius of Kramers. When he applied the Laplacian operator, nabla squared, to the term a dot r to the L, and forced it to equal 0 to satisfy Laplace's equation, the algebra dictated a very specific absolute condition.
Okay, what was it?
It required that the dot product of vector A with itself must equal exactly 0. Mathematically, a dot A equals 0.
Wait, stop. Let's rewind that. A vector dotted with itself is just the sum of its squared components, right? Ax squared plus a y squared plus a z squared equals 0. In standard 3D space, that is literally impossible unless the vector is the origin, 0, 0, 0.
Right.
If a vector has any length at all, squaring the components makes them strictly positive, and they can't possibly add up to 0.
You are entirely correct unless the vector is complex.
Ah, complex numbers, of course.
Yes. If the components of vector A can be imaginary numbers involving I, where I squared equals -1, then the equation ax squared plus a y squared plus a z squared equals 0 is completely solvable with non-zero vectors.
Oh, wow.
Yeah, for instance, if ax equals 1 and a y equals I and a z equals 0, then 1 squared plus I squared plus 0 squared equals 1 minus 1 plus 0, which equals 0.
It feels like a cheat code within a cheat code.
By introducing complex variables, the sources define them as complex parameters. U and V2 construct this complex null vector A. Kramers completely bypassed the need to solve those nasty second-order differential equations.
He didn't have to use the Legendre substitution at all.
No Legendre equations, no worrying about boundary regularity conditions after the fact. By just assuming that algebraic polynomial structure multiplied by a complex null vector, the regularity, the smoothness of the poles, is organically baked into the algebra from step 1. You expand that polynomial algebra when you arrive at the exact same spherical harmonics, purely through polynomial expansion and complex arithmetic.
I point this out because it is such a profound parallel to how a good programmer thinks. When we write code, we often face a choice. Do we write a brute force iterative loop to calculate a value over time, which is essentially what numerical calculus does, or can we analyze the system and find a structural shortcut a closed-form algebraic trick to jump straight to the final state without running the loop.
Right, the O of one solution.
Exactly. Kramers used an algebraic shortcut to arrive at the same orthogonal basis.
And that concept of an orthogonal basis is the linchpin of everything we're discussing today. This brings us to the absolute core of why this math is running on your GPU right now, the orthogonality superpower and spherical compression. We have established that spherical harmonics form a complete orthonormal basis on the sphere. Let's make sure we rigorously define what that actually means in practice.
Let's do it. Orthonormal. Break it down.
It's a portmanteau of two properties. First, normal. This means that each individual harmonic function is scaled perfectly, so that if you square it and integrate it over the entire surface area of the sphere, the total result is exactly 1. It is normalized, just like a unit vector in 3D space having a length of 1.
Okay, so they all carry the same statistical weight. What about orthogonal?
Orthogonal means that if you take any two different spherical harmonics, say the L equals 1, M equals 0 harmonic, and the L equals 2, M equals 1 harmonic, multiply them together, and integrate that product over the entire sphere, the mathematical result is exactly 0 every single time.
The sources refer to this as the Kronecker delta property.
Yes, exactly. Yep. The integral of y sub a times y sub b equals 1 if a equals b, and 0 if a does not equal b.
Okay, why does this actually matter? Why is orthogonality the holy grail for a rendering engineer?
Because it turns integration into a simple projection. Think about a high-resolution 4K environment map of a sunset sky. Millions of pixels of lighting data.
Gigabytes of memory bandwidth.
Right, but because the SH basis functions are orthogonal, any arbitrary function on a sphere like that high-res sunset can be expanded into a simple series of SH coefficients. You just integrate the environment map multiplied by each individual harmonic.
Let me make sure I'm visualizing this correctly. It's like doing a dot product between two vectors to see how much they overlap. But instead of vectors, we are doing a dot product of continuous functions over a sphere.
That is exactly what an integral of a product is. It's a continuous dot product. And because the basis functions are orthogonal, they don't bleed into each other at all. The L equals 1 harmonic doesn't accidentally capture any of the L equals 2 harmonics data. You extract perfectly independent coefficients, let's call them a sub-LM1, for each harmonic shape.
So we are taking a spatial image, a massive array of pixels wrapping around the scene, and we are compressing it into the frequency domain as a tiny, tiny array of floating point numbers.
It is the ultimate spatial compression algorithm. You are no longer storing the individual pixels of the lighting environment. You are storing the fundamental frequencies of the lighting environment.
Which raises an immediate, highly practical question for the programmer listening. If my VRAM budget is tight, and I have a skybox with 10 million pixels, how many of these YLM coefficients do I actually need to store to get a usable, realistic lighting environment in my shader? Because if this requires an infinite series to be perfectly accurate, it's useless to me. Where is the cutoff?
This is where the magic of low-frequency lighting really comes into play. For diffuse lighting, the soft ambient light that bounces around a scene and softly illuminates the shadows, the first few frequency bands are almost entirely sufficient. Let's count them out.
Okay.
The 0-degree band, L equals 0, has 1 harmonic. It represents the total average light of the whole sky. It's just a constant, uniform ambient glow.
So that's 1 coefficient.
The L equals 1 band adds 3 more harmonics, representing the primary directional light gradients along the X, Y, and Z axes.
We're up to 4 coefficients.
The L equals 2 band adds 5 more harmonics, capturing secondary directional gradients and more complex pinches in the light.
So that's 9 coefficients in total.
Yes. And in practice, real-time rendering usually stops right there at L equals 2, or sometimes pushes to L equals 3, which gives you 16 coefficients. 9 to 16 floating point numbers can accurately capture the entire diffuse lighting profile of a 4K environment map.
That is insane.
That is why SH is overwhelmingly powerful for real-time applications. You pre-compute those 9 flows, you send them to the GPU as a tiny uniform array, and your shader has full access to global illumination without casting a single ray.
That sounds absolutely perfect. But wait. There's a massive catch here that we haven't addressed yet. We've been talking about complex spherical harmonics this whole time because, as we saw with Kramers and the exponential waves, the math naturally pushes out complex numbers, imaginary I.
Yeah, complex SH are absolutely essential in quantum mechanics because they encode phase information and angular momentum. If you are tracking the rotation and phase of a spinning electron, you absolutely need complex numbers.
But if I am a graphics engineer writing web GPU, Complex numbers are my worst enemy.
Yeah.
I don't want to store imaginary components in my GPU memory. That doubles my memory footprint instantly for no visual gain.
Right.
Furthermore, I really don't want my fragment shader executing complex arithmetic for every single pixel on a 4K monitor. It will absolutely tank my frame rate. My GPU is optimized for real floats.
Which is exactly why the graphics industry executes a massive pivot to real spherical harmonics. You can mathematically derive a purely real-valued basis by taking clever linear combinations of the complex spherical harmonics and their complex conjugates.
So you basically add them together in a specific way that forces the imaginary parts to mathematically cancel out.
That's exactly the mechanism. The sources detail the exact formulas. By using Euler's formula, which relates complex exponentials directly to sines and cosines, you can add a complex harmonic to its conjugate. The imaginary terms perfectly cancel each other out, leaving you with purely real sines and cosines. The standard convention is that for positive m values, you generate even or cosine-type harmonics. For negative m values, you generate odd or sine-type harmonics.
And this resulting set of real functions corresponds to something chemists use every day, right?
Yes, these real SH functions correspond precisely to real atomic orbitals. If you ever took a high school chemistry class and saw those diagrams of the px, py, and dxy electron orbitals, the shapes that look like dumbbells and clovers, those are literally the real spherical harmonics.
That's wild.
And crucially for our programmer listener, these real harmonics have the memory requirements because there's no imaginary part left to store.
But that's not even the best part. The real superpower of real spherical harmonics is how they map back to Cartesian coordinates in the shader.
This is the pivotal insight for implementation.
Oh.
Because they are real, and because of how the spherical angles theta and phi relate trigonometrically to x, y, and z, the real spherical harmonics align perfectly with Cartesian coordinate systems. You can evaluate them using simple polynomials in x, y, and z.
Let's hammer this point home because this is exactly what the web GPU programmer needs to hear. When you write a shader, you do not want to be computing trigonometric functions, sines, cosines, arctangents, for every pixel just to figure out its polar angles. Trig functions are relatively expensive on a GPU ALU.
Very expensive compared to basic arithmetic. But with real SH, you completely bypass the trig. The L equals 1 harmonics are literally just proportional to the x, y, and z components of your normal vector. The L equals 2 harmonics are proportional to simple products, x times y times z times x squared minus y squared, and 3z squared minus 1.
So let's talk through the actual shader code. I'm setting up my bind group in WebGPU. I pass me my 9 pre-computed lighting coefficients as a uniform array. I'm rendering a pixel, and I know its surface normal vector, which is just a standard normalized XYZ float 3. My shader doesn't do any complex math.
None at all.
It just does basic multipliads. Coefficient 1 times the constant for y, plus coefficient 2 times the constant for z, plus coefficient 3 times x, and so on.
Exactly. You are evaluating highly complex spherical lighting integrals over a hemisphere using nothing but a static lookup table and a few dot products of low-degree polynomials. It is wildly, almost unbelievably efficient.
It's beautiful. It's the exact kind of optimization that makes you appreciate math. But when you are writing these shaders or debugging a 3D Gaussian splatting pipeline that is suddenly spitting out pitch black pixels, you have to be able to picture what you are building. You have to visualize the math to know why it's breaking. The sources detailed a few ways to look at these things: 2D maps, polar plots, and elevation plots.
Visualization is absolutely critical for debugging. If your L equals 2 band has a flip sign because of a typo, you need to know what that looks like physically to spot it. Let's paint an audio picture of one of the most famous harmonics, the L equals 2, M equals 2 harmonic. In chemistry, this is the dx squared minus y squared orbital.
Okay, I'm closing my eyes. I'm picturing my coordinate axes. What does this harmonic actually look like?
Imagine a 3D polar plot, where the distance from the center origin represents the strength or magnitude of the harmonic function at that specific angle. The L equals 2, M equals 2 harmonic has 4 distinct lobes, kind of like a thick 4-leaf clover, all sitting flat on the equator in the xy plane.
Okay, I see it.
But here's the key. They alternate signs. The 2 lobes stretching out along the positive and negative x-axis represent positive values. The 2 lobes stretching out along the positive and negative y-axis represent negative values.
And what's between them? Like, what happens exactly at a 45-degree angle?
Between them are the nodal lines. These are the precise boundaries where the function evaluates to exactly 0. As you trace the circle from a positive x lobe to a negative y lobe, you mathematically must cross a line where the harmonic contributes absolutely nothing.
Let me bring in my favorite analogy for this. I always picture these lobes like a 3D speaker pushing air in a room.
Oh, that's good.
Yeah, so the positive lobes, the ones on the x-axis, are where the speaker cone is pushing air out. The negative lobes, the y-axis, are where the speaker cone is pulling air in. And the nodal lines are the dead zones, the places in the room where the air just doesn't move at all.
That's a highly intuitive physical mapping. And if we translate that back to rendering and lighting, those positive and negative lobes represent where light is actively gathered from or subtracted. If you have a bright light source, like the sun, sitting perfectly in a negative lobe of a specific harmonic, its contribution to that specific coefficient is literally subtracted. If the sun sits exactly on a nodal line, it has absolutely zero effect on that specific harmonic coefficient.
The sources also mentioned elevation-based polar plots as another way to visualize this.
Yes, that's a pseudo 3D mapping technique that can sometimes be much easier to read on a flat monitor. You take a flat base disk representing the theta and phi angles, and you use the physical height z above or below that disk to represent the magnitude and sign of the harmonic. It's fantastic for seeing the undulating waves of the higher frequencies. It clearly separates the positive mountains from the negative valleys.
Okay, so we have the deep mathematical theory, we have the translation to real Cartesian polynomials, we have the visualizations. Now let's bring it all together. How do we actually deploy this in modern graphics? Let's look at the actual master formula of computer graphics, the rendering equation.
The rendering equation, formally introduced by Jem Kajia in 1986. At its core, it states that the light leaving a point on a surface towards your camera is the integral over the entire hemisphere above that point of the incoming light multiplied by the visibility function, meaning, is the incoming light blocked by a shadow, multiplied by the BRDF.
The bidirectional reflectance distribution function, which is, just a fancy way of saying, how does this specific material bounce light? Is it matte like chalk or shiny like plastic?
Exactly.
Yeah.
Now, calculating that massive hemisphere integral for every single pixel, every single frame, is impossible in real time. That integral is the beast that ray tracing tries to tame with massive random sampling. But spherical harmonics offer a magic trick, specifically for diffuse matte materials.
This is the PRT trick, right? Pre-computed radiance transfer.
Yes, the magic trick relies entirely on the orthogonality property we defined earlier. Think about what we're doing mathematically.
Yeah.
We are integrating the product of the incoming light and the transfer function, the BRDF and visibility.
Yes, right.
If you convert the incoming environmental light into a set of SH coefficients.
Those 9 floating point numbers we talked about.
Right. And you also convert the transfer function, how the object bounces light and shadows itself, into its own set of 9 SH coefficients. You have effectively projected both the lighting and the object's physical properties into the exact same frequency domain. When you multiply two SH series together and integrate them over the sphere, all the cross terms, where L doesn't equal L, vanish into zero because of orthogonality. The dreaded rendering integral completely disappears.
Poof. Gone. Replaced by what?
It is replaced by a simple vector dot product. The integral of the products becomes the sum of the light coefficients multiplied by the transfer coefficients, the sum of P sub ij times L sub j.
This is the mind-blowing part for the systems programmer. You have moved the massively expensive calculus integration entirely out of the render loop. If we look at 3D Gaussian splatting during the generation or training phase, the system treats the SH parameters as a continuous multi-dimensional feature space. It's using backpropagation to constantly tweak those SH coefficients for every splat, trying to resolve neural artifacts and match the rendered image to the ground truth photos.
It's an optimization space during training. The network is learning the optimal frequency representation of the view-dependent color.
Exactly. But once the training is done and you package that model and move to the downstream rendering phase, it's completely static. Your web GPU fragment shader simply takes those optimized pre-computed SH color coefficients from the splat, multiplies them by the pre-computed transfer coefficients based on the camera view angle, which again are just those simple Cartesian polynomials, and you get incredibly realistic view-dependent specular and diffuse effects.
All for the computational cost of a single dot product in the shader.
It is arguably one of the most profound and elegant optimizations in all of computer science.
Yeah.
You literally trade an impossible spatial integration for a trivial frequency domain dot product.
It really is.
But, and there is always a but in software engineering, this isn't perfect. We are doing compression, and compression fundamentally means loss.
No.
Let's talk about the limitations.
Yes, bandwidth limits and information loss. Transitioning from a spatial representation like millions of pixels to an SH frequency representation is a form of lossy compression. The sources highlight a fundamental mathematical limitation regarding dimensionality. A spherical function with a bandwidth b has a spatial dimension of O of b squared, but the SH representation only captures a dimension of O of b.
So we're literally losing almost a full mathematical dimension of information.
You have to, because you are truncating an infinite series. A perfect, lossless representation of a sharp image requires an infinite number of L bands. But we established that for real-time rendering memory constraints, we usually stop at L equals 2 or L equals 3. We only keep the first 9 or 16 coefficients.
Right.
By forcefully truncating the series there, you are throwing away all the high-frequency data.
Let's translate high-frequency data into visual terms for the listener. What does it actually look like?
Low frequency is soft, a cloudy, overcast sky. Ambient occlusion in the corner of a room. A broad, blurry reflection on brushed metal. SH is absolutely incredible for that. It captures the soft, sweeping gradients of diffuse lighting perfectly.
Okay, but high frequency.
High frequency is sharp, a crisp, hard shadow cast by a tiny point light. The sharp, blinding specular highlight of the sun reflecting off a polished chrome bumper.
So if I'm building a highly detailed, physically based rendering engine with mirrors and sharp shadows, SH isn't a silver bullet.
Yeah.
If I try to represent a sharp shadow edge with only 3 bands of SH, what actually happens on screen?
You get ringing artifacts. In Fourier analysis, it's known as the Gibbs phenomenon. Because you don't have enough high-frequency waves to mathematically construct a perfectly sharp, straight edge, the math overcompensates. It creates wavy, undulating halos around where the shadow edge should be.
To bring back the 3D speaker analogy, it's like the speaker cone is trying to instantly snap from pushing air to pulling air to create a perfectly sharp sound like a gunshot. But the physical cone vibrates and oscillates as it tries to settle, right? It creates an echo. That echo is your visual ringing.
That is exactly what happens. It overshoots and oscillates. It looks terrible in a render, which is exactly why SH is specifically a tool for the diffuse ambient foundation of your lighting.
So that's why modern rendering engines in AAA games don't use just one technique, they combine them. They use spherical harmonics for the cheap, computationally beautiful ambient global illumination. It fills the room with soft light. And then they layer traditional raycasting or screen space reflections or shadow maps on top to handle the sharp, high-frequency specular highlights and hard shadows.
Exactly. You use the right mathematical tool for the right physical phenomenon. SH handles the low-frequency background effortlessly, and ray tracing steps in for the high-frequency details.
Okay, let's bring this all home. We've gone on quite the journey today. We started with the physical intuition of a stretched rubber sheet and Laplace's relaxation equation. We wrestled with the messy, intimidating calculus of separating spherical variables, only to discover we could bypass it entirely via Cramer's elegant algebraic construction. We adapted that complex quantum math into memory-efficient real spherical harmonics, visualized them as 3D speakers pushing and pulling air, and finally saw how they replace heavy, impossible rendering integrals with elegant dot products in our shader pipelines.
It really is a testament to how deep mathematical theory from the 18th and 19th centuries stuff developed long before the transistor was even a dream, continues to power the absolute cutting edge of 21st century rendering technology.
So, to you, the engineer listening, the next time you pre-compute an irradiance map or optimize a web GPU shader to run a few milliseconds faster or train a 3D Gaussian splatting model to capture a scene, remember what's actually happening under the hood. You are standing on the shoulders of Legendre, Laplace, and Cramer's. You are literally wielding the math of quantum mechanics to paint pixels on a screen.
It has been an absolute pleasure unpacking this architecture with you. The pipelines of rendering are constantly evolving, but the foundational mathematics remain a constant, beautiful source of elegant solutions.
You now understand how we use spherical harmonics to project spatial reality into the frequency domain to save precious compute power. As you go back to your IDE and build the next generation of rendering architectures, ask yourself this. If the frequency domain is this remarkably efficient for lighting, what would it take to design a neural rendering pipeline that bypasses the spatial domain entirely? Imagine a system generating and manipulating objects purely as interacting waves of spherical harmonics, long before a single spatial pixel is ever rasterized. Could the true future of real-time rendering be completely frequency-based? Think about it.